Okay, so we're going to talk about the metabolism of amino acids. I'm in such a good mood because I just gave this lecture, but I didn't turn my mic on. That was the greatest lecture of all time. So I guess this is only a tribute to the greatest lecture of all time. A little Tenacious D reference there. Okay, anyway, so we're going to talk about the metabolism of amino acids. Both the buildup, the biosynthesis, and the breakdown, the catabolism or catabolic pathways. So the first one that we want to start with is deamination of amino acids. So in the deamination of amino acids, we take our typical amino acid and we convert it into a different molecule in alpha keto acid. So we go from alpha amino acid to alpha keto acid. You can see that we have a ketone now in the alpha position. Alpha 2, our carbonyl that was in our alpha amino acid. Okay, so the way this typically actually works is not through a deaminase. There are amino acid deaminations, but in general, this happens first with a transamination event, where we take our amino acid and we react that with a common alpha keto acid, such as alpha keto glutarate. So we have O2 minus C, 1, 2, 3, 4, 5, CO2 minus. Okay, so we have 1, 2, 3, 4, 5. This then becomes alpha keto glutarate. Now, where do I get alpha keto glutarate? Well, with a 5-carbon dicarboxylic acid, that would be glutaric acid, right? 2 is oxalic. Oh my, such good an apple pie. Let's focus on G. G is glutaric acid. So we're looking at the conjugate base of that glutarate. We put a ketone in the alpha position. Alpha on either side, it's a symmetric molecule, and that gives us alpha keto glutarate. So what we're going to do is mix that with a transaminase enzyme and one of my favorite cofactors, PLP. We're going to transfer the ketone to our generic amino acid, and then we're going to put the amine, oops, CO2 minus, excuse me, we're going to put the amine with S stereo control at the alpha position of what was our glutarate to make glutamate or glutamic acid. So we actually form L-glutamate, which is glutamate is appropriate here. But if we're memorizing amino acids, we recognize that name is glutamic acid, and I believe that's E because I think aspartate is D. Okay. Probably wrong. We'll see. And then in any case, the amino acid has now become an alpha keto acid. And that's the first step in most catabolic pathways of amines, is to deaminate the alpha position to convert it into a ketone. We can then do some different chemistry. But the deamination is not really a deamination. It's a transamination because we've transferred the amine from one side to the other side. And notice we get good stereo control. It turns out a lot of these things have exquisite S stereo control to give us our L amino acids. We should be reminded that L amino acids, the L is actually derived from L-glyceraldehyde, which rotates light in the lever rotatory or counterclockwise direction. But plain polarized light could be rotated in either direction by the 20 naturally occurring amino acids. They all happen to be S, and they all happen to look like L-glyceraldehyde, but many of them rotate light in the opposite direction. So it's a little bit of a misnomer to call them L-amino acids, but we're in too deep. 6 years of biochemistry research be gone if we're going to actually call these things by their with the appropriate L and D designation for rotating plane polarized light. And what does it matter? There's like probably one person in the city of Ripon that woke up this morning knowing the vast majority of, or many of the amino acids don't rotate light in the L direction. And that was me. And now all of you. But anyway, my point is it's not that useful of information at the end of the day. Okay, so back to the lecture. Let's get into this mechanism a little bit. Whoops. So in general, as I'm writing out the word mechanism here, the transamination occurs to make L-glutamate, and L-glutamate has very specific deamination protocols to regenerate alpha glutarate, which can then be cycled back into this process to work on all of the other 19 amino acids that need to be deaminated for one reason or another. Okay, so we're doing the mechanism for the transamination reaction. And before we get into that, we should look at PLP a little bit. So PLP is pyridoxal phosphate. I could write that out. pyridoxal phosphate. Okay, so PLP has got, and things that are derived from there have this pyridine ring, and then we have the meat of the molecule, which in this case, because we're looking at the aldehyde form, the pyridoxal, we have an aldehyde at the top. Over here we have O, and if we have a phosphate, that's where the phosphate goes. This OH on the upper right is never touched in terms of being converted into a phosphate, and we have a methyl group coming along for the ride. There was an exquisite level of detail gone into the evolution of this particular cofactor to set everything up nicely. The OH being poised close to the aldehyde allows for efficient hydrogen transfer. If you recall all of those little imine forming reactions where I struggled to think about the hydrogen transfer event and I say, it's not going to happen intramolecularly. We can't go through a 4-atom transition state. By positioning the OH, we stabilize many of these structures and provide a relatively acidic hydrogen for any time we need some sort of hydrogen transfer event to happen intramolecularly. This is especially important when we're doing imine formation within the enzyme active site. Okay, but that's PLP, pyridoxal phosphate. I should add the phosphate at the CH2O position is necessary for a lot of molecular recognition events. And we actually start, PLP is it's often a catalytic cofactor. That means after it does its thing, it's regenerated. That's an important detail. It's a catalytic cofactor, and it's derived from pyridoxine. So pyridoxine looks very similar to pyridoxal phosphate, except the top aldehyde on top of the pyridine, or at the 4 position of the pyridine, is now an OH. Additionally, the phosphate is gone, so this group over here is an OH. And then we still have our OH on the upper right and our methyl group that comes along for the ride in the biosynthesis. Okay, so this is pyridoxine. Pyridoxine is also vitamin B6. So when you have some vitamin B6, you take it, you have some NADH, you do a phosphorylation selectively at one of the oxygens, and then you take usually NAD+, and then oxidize that alcohol into an aldehyde, and you've got pyridoxal phosphate. Okay, pyridoxal phosphate reacts with the enzyme active site. It's usually bound to the enzyme active site by an imine, or as an imine. Let's put it as an imine, sorry. Grammar's not the most important thing today. As an imine with a lysine residue. Okay, so lysine is an amino acid with an NH2 at the end, and we go 1, 2, 3, 4 carbons. I kind of drew that upside down. All right, let's start this way. It's an amino acid, so let's put it into the amino acid form so we control the stereochemistry. Then 1, 2, 3, 1, 2, 3, 4 into NH2. I believe that's right. I'm just gonna, while you're writing that down, let's not mess that part up. 4 carbons. Yep, 1, 2, 3, 4. Perfect. Okay. Wanted to get that in front of us so that we could at least see it. All right. So we have lysine. Now lysine is going to engage PLP. I'm just going to call all of this LYS. And so the aldehyde of PLP, there's the aldehyde, is now adducted to the N of lysine. There's the rest of the residue. Then we still have our OP, we have an OH here, and our methyl group. And that OH is probably providing a hydrogen bonding interaction. Kind of goes on and off, but that really controls the geometry of the PLP cofactor once bound to the enzyme. So PLP bound to lysine. And that's typically how we see PLP occurring in an enzyme. Okay, so now that we have PLP in our enzyme, let's do some chemistry on it. So the first thing that happens in the, now we can talk about the mechanism of transamination. Goodness gracious. Okay, the first thing that happens is Step 1, what we call transemanation. So swap imines is what we're going to do. Okay, what does this look like? Well, let's take our PLP bound to the enzyme. Getting really good at drawing this now. So this is PLP bound to the enzyme, and we call this the internal aldimine. Why do we say aldimine and not imine? It's just to kind of help us with pronunciation and articulation that we have an imine instead of an amine. So an aldimine is like an aldehyde imine. Nobody thinks about that anyway. It's just a way of thinking about an imine or a Schiff base. So this is an internal aldimine because it's within the active site of the enzyme, and the PLP is actually bound to the enzyme covalently at this stage. But that's not going to be for long, because what we're going to do is take the NH2 that's on our carboxylic, on our amino acid, and we're going to adduct with the imine, the internal aldimine, to make this intermediate with 2 nitrogens. All right, so N-lysine over here, OH, and maybe if you want, you could let the, all right, I'm just going to let the negative charge be hydrogen bonding to that OH. Because of that OH, I don't have to worry so much about the protonation state of things. If we need protons, we've got protons. If we need a basic site, we probably have the OH deprotonated anyway. All right, so I am going to let the H pluses sort of transfer. Because it's the big picture that we want to focus on here. I mean, we've got H pluses everywhere. Okay. All right, so we've added into the imine, and now what we're going to do is lose. I should draw that OH covalently bonded, so I can always have a an H to pick up when I need it. But we're going to let the nitrogen that was added from the amino acid make a double bond with the PLP cofactor and push off the lysine residue. So lysine is actually going to be disconnected from the PLP cofactor, and we're no longer covalently bonded as an imine to the enzyme active site. Instead, what we are is an imine from, and then we'll pick up an H plus from all the places we could pick up H pluses around here. We're now an imine or an aldimine bound to the amino acid. So this is called an external aldimine. Okay, what do we need to know about the external aldimine? Well, the key thing I want you to be aware of is that we are strongly acidic at the alpha position. That alpha position I know we've talked about is we know that alpha positions can be acidic in carbonyls, but in amino acids where you have a carboxylate on one end and an amine on the other end, we're not that acidic as compared to a typical alpha position. But once we're bound to PLP, we can be. And the reason why is this: oftentimes this nitrogen is protonated. That allows for us, when this is protonated, that allows for that PLP to bind in the active site without having a covalent attachment to a lysine residue. So let's draw that protonated. So the nitrogen is now protonated on the pyridine ring. And then we can really take charge with pushing arrows here. Okay. At this position, now we can have a base come in. Let's see if the book makes note of what a particular base would be. So it usually has the lysine residue. That's fine. Lysine makes for a good base. But we're going to take that hydrogen and we're going to deprotonate it to make a carbon-nitrogen double bond. That's going to break the octet on the nitrogen because it's already got a double bond. So let's push those electrons down, push those electrons through, and then take this last bit of electrons and make a lone pair on the nitrogen atom. So again, PLP is everybody's favorite cofactor. And by everybody, I mean all the people in the world that like to push electrons with curly arrows. Now, my biochemistry senses, which are developing, tell me we probably don't want this OH to go along for the ride too long, but I'm going to leave it there. Okay, by removing that H+, we now have a neutral structure because we protonated the nitrogen, but we've lost aromaticity on the nitrogen. Okay, it's helpful to see us neutralize the structure, but I got to be honest, this isn't my favorite resonance structure of this molecule. My favorite one has some charge separation, where we push the electrons all back through and put a negative charge at the alpha position. The whole purpose of the PLP cofactor is to stabilize the negative charge that would result if we deprotonated the alpha position of an amino acid. We can't do it without forming that external aldimine. Okay, so we have this negative charge at this position. And what will that negative charge do? Well, the negative charge could do a few things. We could pick up a proton. Now, if we do pick up a proton right there, we just form, I just dropped my pencil, sorry. We just form back the starting material. Now, alternatively, what we can do is we can let the negative charge sort of pick up a proton at the opposite end of the imine. So if we pick up the proton here, we just go back to starting material. But the cool thing about deprotonated imines is they're kind of like an allyl imine, where we can push a negative charge across 3 atoms effectively, and we can push the H+ over to this side. Now, if we do that, we then have a carbon-nitrogen double bond at the alpha position, and we've picked up a hydrogen here. We still have our pyridine. I realize I left some stuff off of my pyridine. Sorry about that. OH, methyl, PLP, or phosphate. Oh gosh. I was like, man, I'm getting really fast at drawing PLP. It's because I was leaving off half the freaking molecule. Okay. All right, so when we do that, we push the H, we put the H+ over on the right side, and we form a new imine. This is sort of like a rearranged external aldimine. Okay, so what this can do is simply react with water, and water can react with imines to make the amine again. This is the reverse reaction that forms when an amine reacts with a carbonyl to form an imine. Now, if you want to write it out, we can, certainly. We can have the water attack in here, and we can use that useful hydrogen atom to get to this intermediate where we've got now an NH plus H2O added plus. Okay, let's just drop that hydrogen off to get back to a neutral structure. The O- is going to be very helpful here for that. The O- on the aromatic ring that I've just gotten tired of drawing. Okay, now this species can lose its other hydrogen and kick off the amine if, I suppose, if we let that amine pick up the H+ that we just lost. Now, when we do that, we form an alpha keto acid, and we're done with the mechanism. But after we finish this mechanism, we now have an NH2 on our PLP. An NH2 on our PLP is not PLP. Rather, this is PMP, pyridoxamine phosphate. It's close, but it's not PLP. So PLP is not regenerated as a result of forming the desired product. Rather, we get PMP. Okay, we got our alpha keto acid, so we're done, right? Well, we wouldn't be able to, continue to cycle this through using a catalytic cofactor if this was it, right? We have to figure out a way to turn over the PMP that's being formed. So to turn over the PMP, that's where we use our alpha keto glutarate. So PMP gets turned back into PLP through, or using, so we've sort of just, using alpha keto glutarate, we've sort of just done half of the transamination reaction. We have to do the other half now, which is where we take the NH2. I'm not going to push as many arrows through this because it starts to get quite redundant. We're going to let this react with perhaps I should have flipped that over. We're going to let this nitrogen connect with this carbonyl to make an imine. It's helpful if I let that NH be protonated within the enzyme active site. Now, when we do that, we get to this species. I had to flip over the glutarate. And we're going to go through the opposite set of conditions to do this. So after we did the imine formation, that's when we released water, whereas in the last step of the transamination to make the alpha keto acid from an amino acid in general, we had to add water in the last step. So here, the first step, we're releasing water as we form our imine. So this would be a different external aldimine. Okay, so what do we do at this point? Well, we're going to sort of cycle the hydrogens around. So I'm going to put a tilde H plus to show that we're moving the H plus. Now, when we do that, the enzyme active site says we're going to just get the S enantiomer. There are some enzymes out there that get the D amino acids, but our exquisite selectivity for our S amino acids comes from the enzyme active site of our PLP using enzymes. All right. So we did that hydrogen transfer with more curly arrows last time. Here I'm just letting the hydrogen transfer from one position to another. And so that was this hydrogen now going to the alpha position. Okay. Now at this point, we have a rearranged external aldimine. Actually, I think the previous one should be the external aldimine, just because I kind of like this being our external aldimine because it puts the imine at the position where the carbonyl is going to form. So sorry, let's call that the external aldimine number 2, because it's this that reacts with water. Actually, it doesn't react with water. It can react with water to release the PLP aldehyde. What it probably reacts with is lysine attached to an NH2. To do a transemanation, resulting in an alpha amino carboxylic acid. So this last step is a transemanation where we react the amine of a different substituent with our imine and form a new imine. This imine is now PLP as an imine with lysine. And we're back to our internal aldimine. So we've in effect recycled our catalytic cofactor. PLP bound to the lysine residue is what we started with and what we needed to continue onward with the cycle. And now we have L-glutamic, not spelled right, glutamic acid. And that's what I said, we needed to have some sort of ketone to accept the amine. So the transamination, the reason why it's not a deamination is the transamination is required so that we regenerate our catalytic cofactor. What's also useful is glutamic acid is a pretty nice alpha amino acid to have lying around. Okay, so what can you do with glutamic acid? So how do we get, let's say we don't need glutamic acid for a translation event. We don't need a protein that involves glutamic acid. So we just have a bunch of glutamic acid and our body's like, hey, we need some more glutaric acid, or excuse me, alpha ketoglutaric acid, alpha ketoglutarate. How do we get back to alpha ketoglutarate? Well, we do an oxidation followed by a hydrolysis. So an oxidative hydrolysis of L-glutamic acid. Okay, so what does that look like? Well, if we just draw 1, 2, 3, 4, 5. So here is our alpha glutamic acid drawn upside down. Now what I want to do is I want to let that react with an NAD cofactor. It says it's, yeah, NAD. So this is going to be NAD plus. And what NAD plus is going to do is serve as an oxidizing enzyme where the alpha hydrogen attacks para to the positively charged nitrogen. And then at the same time, we have a basic residue in the active site, adding to a hydrogen. I'll grab this one for the sake of clarity, pushing down to make a double bond. So the hydrogen gets lost. We swing the electrons down to make a carbon-nitrogen double bond. And to avoid breaking the octet of the carbon, we push the hydrogen atom into the NAD plus, and it takes with it its electrons. That's going to give rise to an unstable imine, which is rapidly hydrolyzed in the presence of water to give our alpha ketoglutarate. And we form some NADH as a result of removing the hydrogen from the alpha position. Okay, so now we're back to alpha ketoglutarate and we can continue the cycle onward. Yeah, we have to figure out a way now to continue to pick up now NAD plus to continue this process onward and upward. But this is one approach to breaking the first step to kind of metabolizing amino acids in kind of a catabolic fashion is doing the deamination process. And then we can sweep through and do some other processes to deal with that alpha ketocarboxylic acid. That's the general approach. Transamination using a catalytic PLP cofactor followed by a non-catalytic cofactor dependent event where we deal with the, we sort of recycle our alpha keto acid that's required. The next reaction, we'll look at the urea cycle, continue to kind of break down these amino acids before we build them up. Until then, we'll see you next time.